This is joint work with Marcus Webb, who funnily enough was my research student in Cambridge, but he never worked on this in Cambridge. I didn't. And we started to work on this only after he finished. And now he is in Manchester. And really the motivation is our search for computational methods for equations of quantum mechanics, for dispersive hyperbolic PDEs. But don't worry, there will be not many PDEs in this talk. But let's start with motivation in which there is some gentle Pde theory. So suppose that we have a time-dependent linear PDE. All this can be generalized to nonlinear PDEs, but I will not go into that. So we have some time-dependent linear PDE. L is a well-posed differential operator. We have some initial conditions, boundary conditions. And we have a sufficiently smooth orthonormal system in L2 of the relevant space. Then a spectral method is simply an approximation of the solution in this basis. So we have the coefficients are time-dependent. At 0, they are determined by the initial condition. And otherwise, we obtain linear ODEs, or in this case, for the coefficients using the Galerkin conditions. So that's it. And spectral methods have several advantages. One of them that really attracted us to this business is that we are interested in solving equations on full space rather than on compact or bounded domains, because quantum phenomena usually don't like to be confined to specific parts of the space. And in that case, the standard numerical methods familiar to every undergraduate, like finite differences or finite elements, simply don't work, or don't work very well. So we want several features from whatever method we're constructing. First of all, we want it to be stable. In other words, the numerical evolution has to be well posed. If it is not well posed, then when the number of degrees of freedom tends to infinity, the computational solution doesn't tend to the exact solution, or may fail to converge to the exact solution. We want conservation of mass. So many equations of quantum mechanics, like linear Schrödinger, nonlinear Schrödinger, Dirac, Wigner, and so on, conserve mass. And this is an essential physical feature, and we want our equation to conserve mass. In other words, for the L2 known to stay constant. And by the way, if this is true, then automatically we have well-posedness. Many of these equations are Hamiltonians, and ideally we want to conserve the Hamiltonian. We want the method to converge fast. So in other words, when we're expanding it in our orthogonal sequence, we want the number of terms to be relatively small, and still we want to get high accuracy. And we want to advance in time very cheaply. So this is a long shopping list, and we believe we can do all of them, but this will not be the subject of my talk. I want to really focus on one very important feature that occurs once we are looking at orthogonal systems and orthogonality with an eye to these features. So suppose that we have a complete orthonormal system in C infinity, also of some metric space. So C infinity intersection, say, with L2. And in that case, there is a natural map taking functions to derivatives. It is simply a linear map. So phi n prime equals some infinite matrix times the phi case. And this matrix is called the differentiation matrix of the orthonormal system. And it has several interesting features. So first of all, and this is the undergraduate lemma, if we have zero Dirichlet boundary conditions or periodic boundary conditions or Cauchy boundary conditions, which is the instance that really interests us, then D is skew-Hermitian. And because it is skew-Hermitian, the exponential of D is unitary, and so we conserve L2 norm. And this is an almost if and only if statement. There is one more instance in which we have skew-Hermicity, which is what we call twisted boundary conditions, when we have finite interval a, b, and phi n at one side is a complex number of modulus 1 times the other side, the value at the other side, and this we regarded as a curiosity, and then we discovered that this is important in condensed matter physics for so-called Bloch waves. And now we want to impose an extra condition on our differentiation matrix, and this condition will pervade the stock. Essentially, the differentiation matrix in one dimension, I'll do everything here in one dimension. You can extend it to several dimensions in different ways. The most obvious is tensor product. There are other ways. But in one dimension, space dimension, we want our differentiation matrix to be tridiagonal. And then we have this sort of relation because of skew-Hermicity. Of course, it can be here, Bn can be complex, and then we have here conjugate, but you can always rotate the system so that Bn is positive. We want it to be irreducible. And then we have here Bn minus 1, Cn is real, and we have this sort of relation. So without loss of generality, we can look at this sort of system. And in case D is real and skew-symmetric, then Cn must be 0, of course, and we have this much simpler system.
What's the reason for the name?
Well, the answer is T was for tridiagonal. We didn't have a good name. We didn't have a name until I started to write this talk. And I sent it to Marcus. Oh, yes, great name. So that's it. If anybody here has a better suggestion, we'll go along.
I'm smiling because I avoided use Kashdam property T in my talk not to get things complicated. That I said. So you compensate for that.
Yeah, yes, it is important avoiding clashes in consecutive talks. Yes, even unintentional. Anyway, so turns out that in each of these 3 or 3.5 cases of Cauchy, zero Dirichlet, and twisted periodic boundary conditions, we can construct a T system, and we can characterize the construction of T systems, and this leads us in various different interesting directions of mathematical analysis. And from now on, I'll look only sort of in periodic boundary conditions, not twisted periodic. It is not a great restriction of generality, but slightly simplified stuff. So one obvious way, well, many things are obvious with the benefit of hindsight. One obvious way of constructing T systems is via Fourier transformation. So take this relation and Fourier transform it. So this var theta n, or theta n, is the Fourier transform of phi n, and you normalize it by minus I to power n. And then turns out that we have this 3-term recurrence relation. And 3-term recurrence relation, there is something about it that every undergraduate knows, and there is something about it that undergraduates don't know. So undergraduates know that orthogonal polynomials obey a 3-term recurrence relation. And that's trivial to prove. What is less known, and it is less known to the extent that has been rediscovered at least 5 or 6 times, and as always, the name of the theorem is the name of the last person to discover it, is the so-called Favart theorem. I think that originally it goes back to the work of Shochat and Tamarkin 100 years ago. Namely, that if we have a system of polynomials, each Pn of degree n, that obeys a 3-term recurrence relation, the Bn's are positive, then there exists a Borel measure d mu with respect to which the Pn's are orthonormal. The measure, by the way, need not be unique, but if it is determinate, it is unique. If it is not determinate, like for example the Stieltjes-Wiegert measure, then we can have a whole continuum of such measures. But this is a tiny technical problem that I'll try to avoid. So in other words, there is at the background of this, there are somewhere orthogonal polynomials. But not only orthogonal polynomials, and simply using orthogonal polynomials here is not enough. Because think about it. Suppose that we have orthogonal polynomials obeying this relation, the three-term recurrence relation, and now I multiply all these polynomials by the same function, any function you want. We have another sequence obeying this relation. So the question is there some clever function that at the end will give us what we want once we transform it back? Well, it is convenient to write the measure in Favre theorem as a Radon-Nikodym derivative times d psi. So the weight function is a Radon-Nikodym derivative of d mu. So we are working in a Schwartz space of generalized functions, but this is not a problem. And as I said, this weight function need not be unique. And now take any non-zero L2 function g, then if you multiply all the Pn's, orthogonal polynomials obeying the three-term recurrence relation, by the same function g, we obtain functions theta n that obey the three-term recurrence relation, and this way we obtain all such functions. Then we map it back, and we have explicit representation of our functions, except that for general g, there is absolutely no earthly reason why they should be orthonormal. But simply plugging it into the Parseval theorem, we obtain at once that the correct function g is the square root of the weight function. And later we'll see that different choices of g give us different types of orthogonality. But the simplest L2 orthogonality is simply take square root of w, of the weight function, and then we have orthogonality. We have orthogonality, but we want another feature, which is completeness. We want the system to be complete in L2. And in general, there is no reason why it should be complete in L2. In general, it is complete in a Paley-Wiener space of L2 functions such that the support of the Fourier transform is in an interval. However, if the support of the original function is on the whole real line, then we have completeness. If the support is not on the real line, and later we'll see examples, we can somehow tile the whole real line by different measures so that altogether we have an orthonormal, complete orthonormal system, and later we'll see an interesting example. So let us see a few examples because they really clarify what's going on. And the simplest one, which is familiar to every physicist, not to mathematicians, are Hermite functions. So we are taking the Hermite weight function, e to minus x squared. Hn are standard Hermite polynomials, which I divide so that there will be orthonormal. And phi n's are simply these functions times e to minus x squared over 2. The reason these polynomials stay only also after Fourier transformation is because these functions are eigenfunctions of the linear Schrödinger, of the free Schrödinger operator. And the Bn's are square roots of n plus 1 over 2. And the Hermite functions are popular in theoretical physics. They can be generalized in d dimensions to d dimensions, so-called Hagedorn functions. They have some lovely features. I will not go into that. Another example which sort of exemplifies why it is important to be So the difference between being in a Paley winner space or in L2 are, suppose that we take the standard Legendre polynomials. So now our interval is minus 1, 1. The weight function is constant 1 in the interval minus 1, 1. We have orthonormal Legendre polynomials, and the transformed functions are very nice functions. They're spherical Bessel functions, which are orthonormal in L2, but are not complete in L2. They are complete in a Paley winner space because the Fourier transform lives in minus 1, 1. And all this can be perhaps interesting in signal processing. It is not interesting as far as I'm concerned. And perhaps the most interesting case, which is known now for 96 years, and since then has been again rediscovered time and again, are the Marquis-Takenaka functions. So let us start from the Laguerre measure. So e2 minus x for x greater equals 0, and transform the Laguerre polynomials, which are orthonormal, transform them, Fourier transform them, and normalize them, and we obtain very, very nice rational functions of this form, except that, of course, they are orthogonal only in a Paley winner space of 0 infinity. So we have to add to this, so the mirror image of the Laguerre measure. The mirror image is the measure which is e to x at minus infinity 0. And the only difference is that the index runs over all the integers rather than over all the non-negative integers. And we obtain this system of orthonormal rational functions with a tridiagonal differentiation matrix. And this system has one magical feature, which accounts for the reason it has been rediscovered so often by Norbert Wiener and many others. Under very simple linear transformation, it maps, when you set x equal half tan t over 2, it maps into a Fourier integral. And because it maps into a Fourier integral, we can calculate it with fast Fourier transform. So remember, we do all this for the purpose of computation. In computation, the holy grail is being able to compute stuff with fast transformations. And here we can do fast FFT with Marquis-Takenaka. Well, once you see it, the next natural question is, are there any other T-systems that can be done with FFT? And the answer is yes, but not much. Essentially, it is a very, very, very mild generalization of Marquis-Takenaka. These are all the T-systems that can be done by FFT. It is sort of Marquis-Takenaka plus a little bit of twists that make very little difference. However, FFT is not only fast transform. There are also fast cosine and fast sine transforms. And also in that case, all such systems can be fully characterized. And essentially, they correspond to this situation. So we take Jacobi polynomials, Pn alpha beta. We apply them to tanh x. We have this weight function to normalize. Gn is simply a normalizing constant, very long and complicated, not very interesting. And we obtain, for every alpha and beta greater than -1, this system here. And when alpha and beta are each plus minus 1/2, we obtain systems that can be computed by either fast cosine transform, when alpha equals beta equals either +½ or -½. So it is Chebyshev polynomials of the second kind or of the first kind. We can compute it by fast cosine transform. If alpha and beta are of opposite sign, then we obtain so-called Chebyshev polynomials of the third and the fourth kind, and we can compute them by fast sine transform. And these are the only systems that can be computed by fast transforms. Okay, so periodic boundary conditions, we can do something similar with periodic boundary. Of course, Fourier transform gives us a diagonal skew-Hermitian differentiation matrix, but we can also do other things. I will jump quickly. Again, something very, very similar. So the example, for example, is the Charlier weight. Now, the point about Fourier that we need measures with, we need atomic measures, measures that have jumps at integers. And an example is Charlier weight. It is, so take positive A, and the measure has as jumps, the weight function is jumps of normalizing constant e to minus a times a to x over x factorial for all non-negative integers x. This is Charlier weight. The Charlier polynomials are well known in statistics. And after some algebra, we can obtain our systems explicitly. So phi n's are of this form. And they have, they are periodic, as you can see, in minus 1, 1. And they span only, they are in a sort of equivalent of a Paley-Wiener space because they span only elements of non-negative Fourier coefficients. But you can append to this the mirror Charlier system, and we obtain a system which is dense on L2 pair of minus pi pi. Zero Dirichlet boundary conditions. This was the last instance. This turns out to be not very interesting. So we can do all that. The problem is that it's very easy to see that if you have a differentiation matrix, and if all the derivatives vanish at a point, then if the first derivative vanishes at a point, because then all the derivatives vanish at a point. So if you have zero boundary conditions, say at minus 1, 1, then all the derivatives have to vanish at minus 1, 1. It cannot be an analytic function. It has to have some sort of essential singularity. For example, a function like this, where a0 is simply a normalizing constant. And the problem is that once we are imposing an essential singularity, then funny things start to happen, just to persuade you. So this is the zeros, first, second, and so on functions. And as you can see, we slowly develop boundary layers, and the approximation power of the system is nil. So this really doesn't work with zero Dirichlet boundary conditions. So this was one way of constructing T-systems. But there is another way. And then I'm trying to bring it as near to algebra as possible so that to interest Hans more. So suppose that suppose that we have this relation, this T-system relation, phi n prime equal this, and we are given the constants bn and cn. Then it is very easy to prove by induction, this trivial exercise, that each phi n can be represented as a linear combination of the first n plus 1 counting from 0 derivatives of phi 0. And the coefficients can be derived explicitly from the bn's and cn's. So simply take any phi naught, take any positive bn's, real cn's, and we can obtain the sequence. The only snag is that there is no earthly reason why this sequence should be orthonormal with respect to anything. And the problem is that we are over-determining our system. Remember, if we have the bn's and cn's, we can find a unique modulo indeterminate measures, but a unique phi 0, simply going back to orthonormal polynomials that obey this recurrence relation, finding the measure, and finding the Fourier transform of, not of the measure, but of the square root of the weight function, and this gives us phi 0. So, and we call phi 0 the seed. So we can find the seed, and then alternatively to using orthogonal polynomials, we can use this formula. So on the other hand, suppose we don't have bn's and cn's. all we have is a seed. You pluck a seed out, a function phi naught out of thin air, sufficiently smooth, not identically zero. Can we find bn's and cn's so that we have a T-system? For example, using this formula. And the answer is yes. So suppose that we have a function phi naught in L2 intersection with C infinity. It is not a zero function. And take the linear space spanned by the first n+1 derivatives of phi naught. And we call it the differential Krylov subspace in deference to Krylov subspaces used in numerical algebra, which are similar, but instead of differentiation, we have multiplication by a matrix. And in that case, first of all, it is possible to prove in all our cases that if we have this sort of relation, that we have this relation here, we can rewrite it in this form. Then automatically each phi n is for any bn minus 1 and cn, no matter what they are, then always phi n is perpendicular to kn minus 2. So in other words, you need to determine bn minus 1 and cn so that phi n is orthonormal to the n minus first derivative of phi naught, and so that it is of norm 1. So we have two conditions for two unknowns, and it is very easy to solve them to find an explicit formula for bn minus 1 and cn. And in deference to an equivalent algorithm in numerical algebra, we call the differential Lanczos algorithm. So we have this commutative diagram. We have here the set of all seeds phi naught, here the set of all determinate Borel measures or classes of determinate Borel measures. So each element here can be either a determinate measure or infinite set of indeterminate Borel measures that give the same Jacobi matrix. Here we have the set of Jacobi matrices. These two here are linked by the Favart theorem. These two are linked by Fourier transform. These two are linked by differential Lanczos. And all this is completely commutative. And what is nice is that this diagram transplants to much more complicated situations as well. So before I go even further, so suppose that we have, so far I used L2, standard L2 inner product. And now let us go as far as we can, so replace the L2 inner product with an arbitrary positive definite bilinear form on R cross R. And suppose that we want to use the Lanczos algorithm, the differential Lanczos algorithm. First of all, we need this relation, and turns out that this relation doesn't hold in general. This relation needs the following. It needs essentially integration by parts. In other words, that the real part of the inner product of f and g prime plus f prime and g, the real part of this has to be always 0. Which is obeyed for L2 inner product. It's obeyed for Sobolev inner product, as we'll soon see. It's obeyed for other inner products. And I'll give you an example. It is not obeyed in general. And here is an example which is dear to our heart. So take the free Schrödinger equation in semi-classical regime. So epsilon is small number. Essentially, it is the square root of ratio between the mass of an electron and the mass of a system in an atomic system. So this is the equation. Sort of in a non-free equation, there will be also the potential part, there's the kinetic part, there will be the interaction potential as well. The general solution of this on the real line is simply a Fourier integral of this form. And we can repeat the entire exercise and do the following. Suppose we have an initial condition, U0. Expand it in some orthonormal system, dense orthonormal system in L2. And now, and this is not a spectral method. It is like a mirror image of a spectral method. In spectral methods, the idea now is that we keep the phi n's constant, and we expand the un hats. Now we keep the un hats constant, and we let the orthonormal system rotate. So in other words, chi n will be the solution of the free Schrödinger equation at time t. And this means that the solution of the equation is of this form here. So in other words, we take our orthonormal system, we expand the solution with respect to the elements of the system. So here we have here, instead of u hat, we take the Fourier transform of the phi n element of the orthonormal system, and we expand the lot. And now chi n is exactly the Fourier transform, exactly the same trick we have done earlier, except that this function g, instead of being square root of the weight function, is multiplied by e to half I psi square epsilon t. But this is not a problem, because the absolute value of g is still square root of w. So we still have orthogonality. We still have a t system. And actually, the coefficients of the t system stay, the bn's and cn's stay exactly the same. All the changes will have a different seed. We are starting from a different seed, but the system remains the same, and we have sort of rotating orthonormal frame of reference whose rotation is dictated by the underlying differential equation. And once we have this sort of equations, we immediately can solve using splittings, using well-known tricks of numerical analysis. We can solve equations like this, like, for example, linear Schrödinger, nonlinear Schrödinger, Gross-Pitayevsky, and many other systems. So, and this can be easily generalized to any number of space dimensions. OK, Sobolev inner products. And this is something that we are still exploring. So suppose that we have a function v, an even function, analytic even, in support of our weight function, and such that the inverse of v is in L2. And all the VLs, the coefficients are non-negative, and the sum is finite. In this case, define this Fourier transform. We have the same Pn's as beforehand, but here, instead of square root of w, we take square root of w divided by v. And I'm assuming that all moments of this function are bounded. And in that case, this set is again a T set, but it is not orthonormal with respect to L2, but is orthonormal with respect to this Sobolev type inner product. Of course, if V0 is 1 and all the other VLs are 0, we'll cover L2. But otherwise, we can have much more exotic Sobolev inner products. And again, it has a tridiagonal skew Hermitian differentiation matrix, and the entire theory applies. For example, for V psi equal 1 plus psi square, we have standard H12 inner product, but we can do more complicated things. I'll skip probably on the construction of them because we don't have the time. We can do the same with non-symmetric measures. Again, we have to splice then the measure on the whole real line using different measures. And again, the same magic triangle commutes. And it commutes because our Sobolev inner product maintains this identity here. So we can start from an arbitrary seed and generate the bn's and cn's, which will be different than before, using the differential Lanczos algorithm. However, and now this, what I'm telling you, is half speculation, half results that we could prove, half results that we couldn't yet, I hope, prove. What about Hamiltonians? So suppose that we have a linear Schrödinger equation for simplicity, and for simplicity in so-called atomistic coordinates, so epsilon equal 1, simply to have less numbers floating around, or less variables floating around. So this is the linear Schrödinger equation. V is a real interaction potential, and this is the Hamiltonian. And other dispersive equations have different Hamiltonians, not necessarily as nice as that. Say, for nonlinear Schrödinger, instead of V times mod u to square, we'll have half mod u to power 4. But all this is well known. And what about differential systems that keep the Hamiltonian intact? So it is again a bilinear form of this form here. And it induces some sort of orthogonality. It might be degenerate depending on the potential. But if V is real and non-negative, this will be proper orthogonality. So what happens then? And there are several questions. The first is, can we orthogonalize everything with respect to the Hamiltonian bilinear form? And the answer is yes, but it is less nice. Because the problem is that we don't have this property, the integration by parts property. This quantity, or the real part of this quantity, need not vanish, and there is absolutely no reason why it should vanish. And hence, even if we form this differential Krylov subspace, we don't have orthogonality properties automatically wired into the subspace. And so the differential Lanczos algorithm no longer works. Instead of this, we can use a differential equivalent of the Arnoldi process of numerical algebra, which is essentially like Gram-Schmidt. And Gram-Schmidt is very unpleasant. First of all, it is unstable, although one can do it in a stable manner, but one has to be careful. And secondly, it is very expensive and very awkward to use. But simply to play with it, it is possible to play with it. But then, of course, as always in this sort of business, it is the Winnie the Pooh contradiction. We want both this and that. We want both honey and chocolate on our bread. So we want to maintain, for example, for solving the Schrödinger equation, both mass and the Hamiltonian. And sadly, this is impossible. So it is possible to prove, first of all, that the only sequence that can be orthogonal with respect to both inner products, both to Sobolev, any Sobolev time inner product, including L2, and the Hamiltonian inner product for linear Schrödinger, is the eigenbasis of a certain generalized eigenvalue or ODE problem, which we can formulate from the Sobolev measure, which will be very, very simple for L2. And for example, for standard L2 and Vx equal x squared, this would give us scaled Hermite functions. But even this is not good enough. We can construct a sequence which is orthogonal with respect to both, even if by some magic you know the eigenbasis. But it will not be orthonormal with respect to both. The scaling kills us. So in other words, you have to choose, do you want to conserve mass, or do you want to conserve the Hamiltonian? You cannot do both. But something funny happens. And by the way, this reminds us of a completely different theorem in a different part of numerical analysis theorem of Gay and Marsden, namely that if you are solving Hamiltonian ODEs, then you cannot conserve symplecticity and the Hamiltonian simultaneously unless essentially you have the exact solution. However, something funny happens to which we don't have an explanation. I'll show you one example, but I can easily now switch over to MATLAB and show you 3-4 other examples like that. So suppose that we take v of x equal e to minus x squared, and our seed is e to minus x squared over 2, the one that spawns Hermite functions in the simpler case, and this is simply a normalizing constant. And then we obtain a lower Hessenberg differentiation matrix. The differentiation matrix is no longer tridiagonal for the Hamiltonian, because we don't have this integration by part property. It is a lower triangular matrix plus one diagonal above the main. This means lower Hessenberg. However, these are the elements, the first 10 by 10 elements. And you can see along the diagonal we have very large elements which are not skew-symmetric but tend very fast to a skew-symmetric. And here under the diagonal we have very small elements. Here there are something like 10 to minus 3. In other examples we have 10 to minus 6, 10 to minus 8. They're almost 0. So in other words, we don't have a tridiagonal matrix, but we have an almost tridiagonal matrix. We don't have a general proof. We have only many examples. I cannot tell you how general this is. How long do I have?
Let's say 10 minutes more.
OK.
7 minutes more. Something.
OK, great. There are several obvious further questions one can ask. First of all, suppose that we have such an orthonormal system, how fast it converges? And the answer is nobody knows. There is, in approximation theory, and by mean nobody, I talk just about with every prominent person doing approximation theory today. And everybody answers, we don't know. The problem is as follows. For more than 100 years, people develop incredibly powerful approximation theory in compact intervals, minus 1, 1. You have, say, analytic function in minus 1, 1. Well, in slightly more, and this is the problem. This goes back to the work of Bernstein 100 years ago. Suppose we have a compact interval minus 1, 1. Suppose that we have a function f, an orthonormal sequence, and both are analytic not only in minus 1, 1, but in an ellipse surrounding minus 1, 1. So in this ellipse here, where rho is a number greater than 1. And essentially, you can expand this ellipse until you hit a singularity. In that case, for largest possible rho like this, we have a geometric speed of convergence. So the coefficients of the expansion in this orthonormal sequence converge like 1 over rho to a power. By the way, if everything is entire, they converge even faster than exponentially fast, but that's beside the point. However, you cannot generalize it to a Riemann sphere. First of all, for example, Hermite functions have a singularity to infinity. A polynomial times e to minus x squared, or x squared over 2. E to minus x squared over 2 has a singularity to infinity on the north pole of the Riemann sphere. And even if we have f, which is analytic, and even we have orthonormal sequence which is analytic in a strip, well, if you require both of them to be analytic on a strip along the real axis, including at infinity, and we'll see examples, it is incredibly restrictive. Essentially, it reduces to trivial functions, to rational functions and nothing interesting beyond that. So I'll give you an example which is quite striking. Take f of x equal 1 over x squared and take Marquis-Takenaka functions. Marquis-Takenaka are nice rational functions. They have a multiple pole at minus I. minus 2i. So they are analytic on a strip, including at infinity. Our function is analytic in a strip minus I to I and at infinity. Everything is fine, and I can give you the explicit expansion. Rho equals 3. So we have incredibly fast decay. The decay is like 1 over 3 to a power. And here is an example, 2n plus 1 terms, n equal 10, 20, 30, and 40. And see how fast it decays. Here already you have 10 to minus 20, the accuracy. So this is the error, the absolute value, or the log to base 10 of absolute value. So this means that we have 20 significant digits. Incredibly rapid convergence. Compare this to Hermite functions. For the same function, Hermite functions have a singularity at infinity, and this is the error, again, to log basis for Hermite functions. Here is 0.025, and when you go to 161 coefficients, it is 0.0012. Incredibly slow convergence, and actually the convergence is like 1 over n to 4/3. So a little bit better than linear. Completely useless. And you look at this and you say, wow, Marcus Takenaka wins, and the big, big win. Okay, let us make one tiny change. Instead of 1 over 1 plus x squared, take sine x over 1 plus x squared. What can go wrong? Sine x is an entire function. On the whole real line, it is bounded by 1 by modulus. What can go wrong? And here is the error for Marcus Takenaka, the one that tended like 1 over 3 to n. The error tended to 0 incredibly fast. And this is the error for the same number of terms, and it is as slow as Hermite. And the reason is sine x is not analytic at infinity. And this kills us. And Andre Weidemann computed several functions using steepest descent analysis. Now, everybody hates steepest descent, and everybody is right. It is incredibly messy. For every function, we need to do the analysis all over again. Some people, so Philippe Flageolet and Bruno Salvi, tried to automatize this using symbolic algebra, but this doesn't go far. So essentially, it is plenty of work for every new function. So nobody really likes it, but Andre, with great forbearance, computed the speed of convergence for some functions, and here it is. E to minus x squared decays sub-exponentially, 1 over cosh decays sub-exponentially, but a different coefficient. Sine x over 1 plus x squared, the one I plotted earlier, exactly like Hermite. Like Hermite for 1 over 1 plus x squared. Sine x over 1 plus x to 4, and so nobody knows the general pattern. It is an open problem. However, actually we want more than that. So remember, go back to the very beginning of my talk. I'm really interested. The reason for my original interest in this whole business is solving dispersive equations, computing dispersive equations for quantum mechanics, in particular in semi-classical regime. And in that case, it is known that the solutions, at least in short time, can be composed. It was proved by Christian Lubich, can be composed out of wave packets. This follows from the Born-Oppenheimer adiabatic approximation to a Schrödinger equation. And we can compose the solution as a linear combination of wave packets. So in one dimension, this will be functions of this kind. We don't know the alpha, we don't know x0, we don't know omega. We don't know how many wave packets. Omega is, roughly speaking, 1 over epsilon. So it is a large number. We have very rapid oscillation and slow attenuation. So we have functions like this. And this, it is important to understand these are not solitons or something like this. They don't obey any sort of conservation laws or shape conservation laws and so on. Following various quantum events like quantum tunneling or quantum scattering, wave packets can be born, can decay. We can have one packet, and suddenly instead of one packet, we have quantum scattering, and we have 157 wave packets. And they go all over the place, to the left and to the right, or stand still. There is no much reason to wave packets. But the basic question is, how well are we doing with wave packets? Suppose that the solution is wave packet, how well are we approximating wave packets? So together with Marcus and with my student Karen Luong, we did quite comprehensive analysis for various types of functions. In particular, first of all, we tried stretched Fourier expansions. Suppose you take a Fourier expansion, you stretch it to a very large window, and then everything depends on the size of your window. And turns out that this is really wonderful if you have one packet. If you have more than one packet, it completely collapses. And we did it for Hermite functions on Markowitz-Takenaka. So here is a result. It is one of these results that take 40 pages of nasty algebra, not particularly illuminating, but at the end you have a nice formula. So say for Markowitz-Takenaka, the nth expansion coefficient is sum of two components which essentially decay exponentially fast, but they decay exponentially fast only as long as n is less than a constant times omega. Remember, omega is this large number. It is 1 over epsilon. So in other words, we have this funny situation, which is typical to steepest descent analysis, and somehow goes outside mathematical reasoning. We have an approximation that we know sooner or later will decay very slowly. Sooner or later will decay slightly better than linear. However, it decays exponentially fast until it reaches sizes which are well under any interest of practical mathematics. Until the coefficient is 10 to minus a million or so, it decays exponentially fast. And then it starts decaying very, very slowly. And in practical computations, you can never even show an example. And it is the same true for Hermite, except that in that case, the inequality is too long for a slide and doesn't add much to illumination. It doesn't illuminate much. And the fit is fantastic. So here is this inequality. And let us draw the coefficients, again to log basis, because things here are quite small, and our estimate. And as you can see, it is virtually perfect. And OK, this is exactly perfect time to stop. OK.